Morning students, welcome to our physics class. In the previous classes, we discussed the chapter Human Eye and Colorful World. So in this chapter, we discussed refraction through a glass prism, dispersion by glass prism. Okay, then we discussed the applications of dispersion, rainbow, we discussed. Okay, so in the today's class we have to discuss the topic. Topic scattering of light. We are familiar with the scattering of light. There are many applications for the scattering of light. The blue color of the sky and red color of the sun at sunset and sunrise, we can explain using scattering of light. So what is scattering of light? Scattering of light. When light falls on small particles, when light falls on small particles in the atmosphere, the light scatters in all directions. That is called scattering of light. For example, when a beam of light falls on a small particle in the atmosphere, for example, dust particle. When light falls on this dust particle, it scatters. That phenomenon is called scattering of light. Okay, the scattering of light depends on many factors. The scattering of light depends on size of the particles. Okay, then nature of the color of the light. We know the light constitutes 7 colors. What are the 7 colors? Violet, indigo, blue, green, yellow, orange and red. These 7 colors scatters in different ways, in different manner. Okay, so we can explain it in detail. So due to the scattering of light, light scatters in all directions. We know there are 7 colors: violet, indigo, blue, green, yellow, orange and red. What are the properties of these colors? Violet, low wavelength. Low wavelength color is violet. High wavelength color is red. High wavelength color is red. And all other colors are arranged in between these two. Okay, so wavelength increases. Wavelength, it is denoted by a letter lambda. Denoted by a letter lambda. Wavelength increases from left to right. Decreases from right to left. So low wavelength color is violet. High wavelength color is red. Thus intensity of scattering is inversely proportional to the wavelength. Intensity of scattering inversely proportional to wavelength. Intensity of scattering or amount of scattering is inversely proportional to wavelength. Okay, so which color scatter more or which color scatter least? Which color scatter more? Low wavelength color scatter more. High wavelength color scatter least. So among the 7 colors, which is the more scattering color, which is violet, indigo, blue. Okay, in the case of violet, indigo and blue, high scattering. High scattering colors are violet, indigo, blue. Low scattering colors are yellow, orange and red. Okay, so what is the relation between scattering of light and wavelength? Scattering of light is inversely proportional to its wavelength. Okay, when wavelength increases, low scattering. Wavelength decreases, high scattering. Okay, so we can say more scattered colors are violet, indigo and blue. Least scattered colors are yellow, orange and red. So using these informations, we can explain the blue color of the sky and the red color of the sun at sunset and sunrise. So scattering of light depends on wavelength first. Second is scattering of light depends on the size of the particles in the atmosphere. Okay, very fine particles scatters low wavelength colors. Very fine particles scatters low wavelength colors. Very high particles, large particles in the atmosphere scatters high wavelength colors. But in the atmosphere there are many small particles like dust particles, small water droplets, smoke and fog. Okay, these all are the very fine particles. These very fine particles scatters low wavelength colors. Clear? So the scattering of a particle depends two factors. Number one, wavelength. Number two, size of the particles present in the atmosphere. Wavelength and scattering of light is inversely proportional. Okay, very fine particles scatters low wavelength colors. Very large particles scatters high wavelength colors. Clear? Okay, so very fine particles present in the atmosphere scatters low wavelength color like blue. So blue color is more scattered color by the very fine particles. By the very fine particles, blue color scatters more. Red color scatters least. Okay, so using this information, we can explain the color of the sky. Applications. Applications of the scattering. Number one is color of the sky. What is the color of the sky? Color of the sky is blue. Why? Why the color of the sky is blue? Okay, so we can explain using the size of the particles. We know the size of the particles in the atmosphere is very fine. Very fine particles are contained in the atmosphere. For example, dust particles, very small water droplets, gas molecules like hydrogen, oxygen, nitrogen, etc. Okay, so in the very fine particles, which color scatters more? Blue color scatters more when it strikes on the very fine particles. So blue color scatters more and it spreads in the sky. That's why color of the sky is blue. Blue color scatters more by very fine particles present in the atmosphere. Then the wavelength of the blue color is low wavelength. Low wavelength color, high scattering. Okay. Then the second factor which depends on the scattering is size of the molecules. Very fine particles present in the atmosphere scatters blue color more. That's why color of the sky is blue. Okay. Next, what is the color of the sea? Color of the sea. The color of the sea is also blue color. Why? It is by the reflection of light. Okay, blue color of the sky is reflected by the water contained in the sea. That's why the color of the sea is also blue color. Okay, clear. Next, second application of the scattering is red color of the sun. Red color of the sun at sunset and sunrise. At sunset and sunrise, sun is very far away from us. Okay, at the sunset and sunrise, sun is very far away from us. Okay, so red color reaches our eyes without scattering. We know which color scatters least among these seven. So we know violet, indigo, blue, green, yellow, orange and red. Among these seven colors, which color is least scattered? That is red. Red, least scattering, or we can say no scattering. That's why it reaches our eyes. Okay, at the sunset and sunrise, sun is very far away from us. So light has to travel a long distance before reaching our eyes. Okay, due to least scattering or due to no scattering, this red color reaches our eyes. All other colors are scattered and spread in the sky. Okay, so violet, indigo, blue. These three colors are more scattered colors. So it is spread in the atmosphere. Okay, then which colors reaches our eyes? First, red color reaches our eyes. Then yellow, orange. The combination of yellow, orange and the red color is called reddish color. So at the time of sunset and sunrise, sun appears red color or reddish color. Why? At the sunset and sunrise, sun is very far away from us. So light has to travel a long distance before reaching our eyes. So least scattered color reaches our eyes. Clear? These are the two main applications of scattering of light. Okay, we know danger signals. What is the color of the danger signals? Danger signals are red in color. Red color is used in danger signals. Why? Red color scatters least or there is no scattering to red color, so it reaches a very long distance without scattering. That's why all danger signals are red in color. Okay, which properties of the red color is used in this case? Red color, high wavelength color is red. So there is no scattering or least scattering. That's why it travels a long distance. That's why red color is used in danger signals. Clear? So we discussed first scattering of light. What is the scattering of light? When light falls on the fine particles in the atmosphere, it scatters in all directions. That phenomenon is called scattering of light. The white light or sunlight constitutes 7 colors. What are the 7 colors? Violet, indigo, blue, green, yellow, orange and red. Okay, so the scattering of light depends 2 factors. Number 1, wavelength. Number 2, size of the particles. Clear? So what is the relation between wavelength and scattering? The intensity of scattering is inversely proportional to its wavelength. Okay, scattering of light depends on size of the particles. Okay, on very fine particles, this low wavelength color scatters more. High size particles, high wavelength color scatters. Okay, so in the case of atmosphere, it contains dust particles, gas molecules, very fine water droplets, etc. Okay, these all are the very fine particles. In the very fine particles, which color scatters more? Blue color scatters more. That's why color of the sky is blue. At the sunset and sunrise, the sun appears red color. Why? At the sunset and sunrise, sun is very far away from us. So light has to travel a long distance to reach our eyes. Okay, so red color, which is high wavelength color, scatters least, or it travels a long distance without scattering. That's why red color is used in danger signals. In signals or danger signals, red color is used. Clear? So these are the applications of the scattering of light. Next topic is Tyndall effect. Tyndall effect. So Tyndall effect is discussed in the 9th class. What is Tyndall effect? Tyndall effect is the scattering of light in the colloidal particles. Scattering of light in the colloidal particles is called Tyndall effect. For example, in the case of a smoke filled box, we take a smoke filled box. Then when light passes through this smoke filled box, the path of the light is visible. That phenomenon is called Tyndall effect. In the case of Tyndall effect, when light passes through the colloidal particles, the path of the light is visible. Okay, example is when light passes through a small hole. Okay, a small hole in a smoke filled room or a smoke filled box, the path of the light is visible. That phenomenon is called Tyndall effect. Another example is when light passes through a canopy of dense forest. When light passes through a canopy of dense forest, the path of the light is visible. That phenomenon is called Tyndall effect. Tyndall effect means it is the phenomenon of path of the light is visible. Path of the light is visible due to scattering. That phenomenon is Tyndall effect. Okay, we can explain an activity, okay, for scattering of light. First we take a beaker. We take a beaker. It is filled with fresh water. 2 liters of fresh water is filled. Okay. Here is a source of light. Yes, source of light. When this light is on, this light passes through this solution. Here we placed a cardboard with a hole. Cardboard with a hole. A cardboard is used. Okay. Then here a convex mirror, convex lens is used. Here, convex lens, cardboard. Okay, here is one beaker. It contains 2 liters of water. Then here a screen. This is the experimental arrangement. Okay, first we take a beaker. It is filled with fresh water or clean water. Here a source of light is used here. Okay, then here is a cardboard with a hole. Then a convex lens parallel to this cardboard and a screen is placed parallel to the convex lens. Okay. When this switch is on, what happens? Light passes through the solution and reaches in the screen. Here white light is used. When white light from a monochromatic source is passes through a solution, or solution means clean water, it passes through this hole and it passes through this convex lens and it converges to a point. It converges to a point on the screen. So here white light is used. So we get white light on the screen. Okay, this is the first step of the experiment. In the second step, we add to this true or clear water 200 gram of sodium thiosulfate. 200 gram of sodium thiosulfate is dissolved in this clean water. So now it is a sodium thiosulfate solution. Okay, so first clean we take fresh water or clean water, then add 200 gram of sodium thiosulfate to this clean water and it is dissolved in it. Then we add 1 or 2 ml of concentrated sulfuric acid. 1 or 2 ml of concentrated sulfuric acid is added to these solutions. Then what happens on the screen? When we add 1 or 2 ml of concentrated sulfuric acid to these sodium thiosulfate solutions, sulfur particles are formed. What happens? When 1 or 2 ml of concentrated sulfuric acid is added to this sodium thiosulfate solution, sulfur particles are formed. Sulfur particles are formed. When this white light passes through this solution, now this light falls on the sulfur particles and it scatters. Okay, these sulfur particles are very fine particles. So blue color spreads in this solution. So this solution is now blue color. Okay, then red color passes through these and reaches the screen. So in the screen, red color reaches first on the screen. Then orange color reaches on the screen. Then yellow color reaches on the screen. All other colors scatters. Okay, then without scattering, first red color reaches on the screen. Why? So red color, yellow, orange, red colors are least scattered colors. Which color is most scattered color? Here blue color is most scattered by very fine particles. So in the first part of the experiment, white light is reached on the screen. In the second step of this experiment, red color, orange color, then yellow color reaches on the screen without scattering. Okay, so on adding 1 or 2 ml of concentrated sulfuric acid to the sodium thiosulfate solution, a very fine particle, that is sulfur particles, are formed on this solution. On striking light on the sulfur particles, blue color scatters more, so blue color spreads in the solution and all high wavelength colors like red, orange, yellow reaches on the screen. So in this experiment we clear that in the very fine particles, blue color scatters more, red color scatters least. Clear? So this is the end of this chapter. So in this chapter we discussed refraction through glass prism, dispersion by glass prism, then applications of dispersion, then atmospheric refraction, its applications, then scattering of light, its applications. Clear? Okay, so this is the end of this chapter. So today we can conclude our class. Okay, thank you.